In this particle chapter, the concept of radioactivity is included again. And in basic concept of radioactivity that we already studied in the previous course, that radioactivity is the concept of emission of radiations from unstable nucleus. Because when the nucleus of any atom or any element is unstable, so it starts to emit out extra mass or extra energy from the nucleus, and that process of emitting out extra mass or energy is called radioactivity. So it is the phenomenon of emission of radioactive radiations from the nucleus of an unstable atom, of an unstable nucleus or atom. And in periodic table, if generally we talk about, so all the elements beyond lead are radioactive, naturally radioactive. We can also make them artificial radioactive material by adding extra neutrons in their nucleus, just like the fission reaction. But beyond lead, in periodic table, if we observe, so all elements beyond lead are naturally radioactive. They can emit radiations naturally by their self. And one more thing, this radioactive phenomena is actually random and spontaneous. So first property of this reaction is that it is a random process, and it is random process means that if we talk about all the radioactive atoms or all radioactive elements, so we cannot predict their uh, process pattern or like at what time they starts to decay. So it is difficult to predict any specific time or any specific pattern for the radioactive emission, right? So it is completely depending upon their own nature. So every nucleus has equal chance to decay, and it cannot be predicted which nucleus is going to decay when. So it is completely unpredictable process. So there is no specific pattern, no specific time duration for this radioactive emission process. And the second property of this radioactivity is spontaneous. Spontaneous means if we consider external conditions, like if we increase temperature of the surrounding, if we place this radioactive material into the freezer or in like a very high temperature, specific high temperature place, so there will be no effect of this high temperature or low temperature on this radioactivity process. So it means this process is spontaneous. There is no effect of any external condition on this radioactivity process. So for spontaneous, by changing external condition like temperature and pressure, has no effect on its activity. So this is the concept of spontaneous. And as we already know, there are three types of radiations. The first one is alpha, second is beta, and in beta we need to study two more process, beta positive and beta negative. So specific now in this course we need to study these two process individually. So beta positive means positron, negative means electron. So in previous course, we know that beta decays into a fast moving electron. So with the concept of fast moving electron, we know about beta negative decay. But beta positive is also in the category of beta. So we will also discuss what is the difference between these two processes. Third is gamma rays. So these are the three categories. And first of all, if we start with alpha, so for alpha rays, we know that for alpha ray, the symbol we use or the nuclear symbol we use for alpha is equals to this symbol, Greek symbol alpha, 2, 4, and the nature of alpha that it is equals to helium nucleus. So it is equals to helium nucleus, 2 protons and 2 neutrons. And there is also a +2 charge on this alpha. And if we talk about ionization power, so ionization power is greatest in alpha. Greatest ionization power. So greatest ionization power, because of greater mass and greater charge, it can easily like gain electron or lose electron with the help of the alpha rays. And penetration power is weakest because it is heavy and greater in size as compared to beta and gamma. So that's why it will be difficult for alpha particles to pass through any specific material. So it means penetration power. And if we talk about the roughly range of the alpha rays, so range is approximately like maximum 10 centimeter, but on average we used to consider 4 centimeter to 5 centimeter. But maximum if we consider, so it will be approximately equals to 10 centimeter. And if we talk about the equation, so for example, if we consider uranium 92, 235, and it decays into alpha 2, 4, and rest of the values is going to be added up into the new material or the element 90, 231. And definitely we will also get amount of energy. So this is the concept of alpha rays. And for beta rays, as we mentioned, beta negative and beta positive. So first, if we talk about beta negative, because we are already familiar with beta negative. So symbol for beta negative is equals to this Greek symbol beta with -1, the value of electron, and 0 for number of neutrons. And beta can be considered as fast moving electron. So it is equals to fast moving electron, and charge is equals to -1. And for the ionization power of beta is less than alpha, but penetration power is greater than alpha. Alpha. And if we talk about the range, so the approximate estimation for the range of beta is in meters, or like 10 meters approximate value. And for equation, we will compare with the equation of beta positive. So first of all, if we talk about beta positive, then we will compare the equations of both. So the next category is beta positive. So for beta positive, we can write +1 and 0 number of neutrons. So this is the symbol for beta positive, and it is also fast moving positron. Fast moving positron. And positron, if you remember, it is the antimatter of electron. So it is like the opposite matter of electron. So that's why it is called beta positive, exactly opposite to beta negative. And we are getting antimatter, that is positron. Positron is the opposite of electron. And charge will be equals to +1. And ionization is same, less than alpha. And penetration greater than alpha. And if we talk about the range, so the range of beta positive is not very much high, just like the beta negative. So the range of the beta positive is less. Short range. And now if we consider equations, the equation for beta negative decay and equation for beta positive decay. So for the negative one, for example, if we consider uranium 92, 235, it decays into beta negative, another particle 93, 235 plus this element. And if you remember, it is called anti neutrino. So this element is actually antimatter. So this is actually anti-neutrino. And in the same way, if we compare with beta positive, uranium 92, 235, it decays into beta positive with one more particle, 91, 235 plus neutrino. because we are already using antimatter of beta negative, so that's why we are already getting antimatter in the equation of beta negative. So this time we will get only simple matter, not antimatter. So both are exactly opposite to each other. It is called neutrino. And further, if we differentiate between beta negative and beta positive, so if we talk about beta negative equation, we have one neutron, let's suppose. So basically, in beta negative decay, this neutron converts into one proton, one electron, that is beta, basically beta negative, that is electron, and also in anti-neutrino. So basically, this is the equation of beta negative decay. So this neutron converts into one proton plus beta plus anti-neutrino. So basically, the difference between beta negative and positive is not just like a positron and electron. There is also a difference in the process. Like in this process, neutron converts into one proton and one electron. So neutron converts like this. And if we consider the quark model equation, so in quark model equation, it is equals to, because we are only talking about neutron. So in neutron, the structure will be up, down, down. And for proton, it is up, up, and down. So basically, we have one more down quark in neutron, and we have one more up quark in this proton. So according to this D is equals to U beta negative plus anti-neutrino. So this is the quark model equation, right? Any confusion in this? Because we have two down quarks in neutron, and one down is like greater than the proton, and we have one more up quark in proton as compared to the neutron. So this is the concept of beta negative and its quark model equation. And in the same way, if we compare with beta positive, So in beta positive decay as compared to negative, in negative we convert neutron into proton and electron. But right now in beta positive, one proton gives you one neutron and positron with only neutrino. And for this process, equation will be equals to 1p, 1 proton gives you neutron plus positron and neutrino. So this is the equation for beta positive, and this equation is also balanced completely, just like the beta negative equation. And in this scenario, quark model equation, the quark model equation will be equals to up, because we have one more up quark in proton and one more down quark in neutron plus beta positive and neutrino. So this is the equation for beta positive. So this is the difference between beta positive and beta negative decay within the reference of the equation and with the reference of the particles conversion, that how one particle converts into the other one. And the last process is for gamma rays. So for gamma rays, we use the symbol like this. And the nature of gamma is high frequency electromagnetic radiation. Radiation. And there is zero charge, no mass. And if we talk about penetration power, so penetration power is greatest. Least ionization power, and it can be stopped by a lead material or concrete material. And if we talk about the range, so range is about several meters, approximately 50 meters maximum. And for equation, same uranium 92 235, it converts into uranium plus gamma radiation. So equation is same, but there is one difference. This first one is excited element or unstable, but the second one is stable. And from gamma, we are only getting energy, right? So these are the properties of alpha, beta, beta positive, negative, and gamma. And in this all type of nuclear reactions, there are some quantities that remains conserved. So if we talk about quantities that remains conserved during nuclear reaction, so first of all, we have proton number. So in equations, we observe that proton number remains conserved, mass number, charge, momentum, and the very less value of mass that converts into the energy, the concept of mass energy conversion. So the very less amount of mass that decays, it converts into the form of energy. And we can also use the concept of another unit of energy. Normally, we mention energy in joules. Work done can also be represented in joules, but we can also calculate energy with the unit of electron volt. Electron volt. It is also a unit of energy, and it is like a type of energy, we can say. When an electron is accelerated through a potential difference of 1 volt. So basically, there is one electron and 1 volt of potential difference is applied on the charge or with that one electron. So the amount of energy gained by one electron when voltage of 1 volt is applied on it, so that is equals to 1 electron volt. And 1 electron volt is equals to the value of electron is 1.6 10 to the power minus 19 joules. So the value of 1 electron volt is equals to 1.6 exponent minus 19 joules, because the value of electron is 1.6 into 10 to the power minus 19. And from all these concepts, if we consider some past papers questions related to the particles. Okay, so first of all, we have question number 7 related to the particle concept. So we have one element fluorine 18, and it is an isotope that decays to an isotope of oxygen. So one isotope decays to another isotope by emission of beta positive particle. So we need to complete this nuclear equation for this decay, including all the particles involved. So it is related to beta positive. So we know that it emits into isotope of oxygen. But first of all, if we write down the values of um, beta positive particle, so it will be +1, 0, and neutrino. So the value of oxygen will be equals to 8, 18. So this is the equation for this fluorine that decays into isotope of oxygen with beta positive particle decay. Second part, a quark in fluorine 18 nucleus changes flavor during the decay. State this change of the flavor. So basically in this we need to show which flavor converts from one quark to another quark. And according to the equation of beta positive, in beta positive we discussed that initially we have up quark and finally it converts into down quark, right? In beta negative we started from down quark and it converts into up quark. So these quark model equation helps to answer this question. So up quark converts into the down. So this is the answer of this question. Part B, a hadron has a charge of -2e, where E is elementary charge. It means charge of electron. State and explain whether the hadron is a meson or a baryon. So basically the value of hadron is, the charge of hadron is -2e, and E is the elementary charge. So we need to explain this hadron with charge of -2e is equals to a meson or a baryon. So basically, if you remember, when we divide into the categories, so in the categories of hadrons, we have two further branches, baryons and mesons. So in baryons, we have three quark system, but in mesons, we have two quark system. And in baryons, we actually work with three quarks, and in three quarks we observe that the negative value is equals to minus 1 over 3, and the positive value is equals to plus 2 over 3e. So basically, if we consider the category of mesons, so we have only two quark system, and two quark system means it will give you only a charge of 0 or like plus or minus 1. So that's why we can identify that this category of hadron is equals to the baryons, because in baryons we can get the charge of minus 2e. So basically we can say, so the value of charge and minus 1 over 3e. So basically when we are working with the category of baryons, we have to like add minimum 3 quarks, because baryons is the setup of 3 quark system and mesons is the setup of only 2 quark system. And from the question, we are working with beta positive decay. Beta positive decay is itself antimatter. So in the same way, if we add 3 anti-quarks, right? So from 3 anti-quarks, we will get answers also. For example, if we add 3 anti-quarks, so if we add them, so we will get answer minus 6 over 3 equals to minus 2e. So basically, if we add anti-quarks, just like minus 2 over 3, 3 anti-quarks, so it will gives you answer minus 2e. Because we are using antimatter, so that's why we use the concept of anti-quarks also. Because if we add a simple quark value 2 over 3, it will give you answer 6 over 3, that is positive 2e. So now it is proved that if we need to find out this value of minus 2e, so we need to add 3 anti-quarks. Minus 2e. And if we consider mesons, so in the category of the mesons, they can only have a charge 0 or plus minus 1. So this is the maximum and the minimum value we will get from any type of mesons. And in second part, state a possible quark composition. for the hadron. So just like in the previous part we already discussed, we need to add anti-quarks. So from the concept of anti-quarks, there are multiple choices. For example, we can add like anti-up, anti-charm, or anti-top. So when we add them, so it will give you same value because we have plus 2 over 3 for up, plus 2 over 3 for charm, and plus 2 over 3 for top. So if we add anti with them, anti up, anti charm, anti top, so it will be equals to minus 2 over 3, minus 2 over 3, minus 2 over 3. So basically, the possible quark composition will be like anti up, anti charm, anti top, like this. Okay. So if we add them in any combination, because right now we are not writing down exact values because the values for the quark of a specific element is not given. So possible quark combination will be like any three of them, right? Any confusion in this? So basically it depends upon the classifications that we discussed. So it is very easy concept and question is also for 7 mark only. So you will get short questions like for 7, 6 or 5 marks from this chapter. 6. This time it is from 2021 because it is from old syllabus. So we got 10 mark question. Kinetic energy and this concept is also included. So we will further practice the questions from this chapter in next class also, and also the MCQs. But the important part in this whole chapter is to know about the classifications, the difference between classifications, and the concept of alpha, beta positive and negative decay. Because these two concepts are new in this AS, alpha and gamma and simple beta decay is same just like the previous course that we studied, right?